Section 2.6, Mathematical Models and Building Functions. I'm going to work out a couple of examples just so that you can have them as reference. These are similar to your homework. A right triangle has one vertex on the graph of y equals 9 minus x squared, only x greater than 0, at x comma y, another at the origin, and a third on the positive x-axis at x comma 0. What we're going to do is we're going to express the area A of the triangle as a function of x. Okay? In order to start, we're going to build, or we're going to draw a picture of this. The graph 9 minus x squared is a parabola with its origin at 9, 0, and it's been flipped over the x-axis. We have a right triangle with one vertex at the origin, one at some point on the positive x-axis at x0, and then another point on the graph of y equals 9 minus x squared at xy. Notice that the x-coordinates of x0 and xy are the same, which is why they are lined up vertically. And here's our right triangle. We're interested in finding a formula for the area as a function of x, so in terms of x. Now, the formula for any area of a triangle is 1/2 base times height. Since this triangle is a right triangle, we can use its two legs as B and H. I'm going to redraw my right triangle without the function graph, just for simplicity's sake, putting the vertices where they are, and labeling B and H. So in order to write the area as a function of x, we need to write B as in terms of x and H in terms of x. All right. Well, we have a formula called the distance formula that tells us how long a line segment is. So I can find the distance or the length of B by taking the square root of the difference of its x-coordinates of the endpoints, oops, pardon me, that's not a comma, x minus 0, and squaring them, and adding the difference between the y-coordinates of its endpoints, squaring. This becomes x squared plus 0 squared, which is just 0, so this is the square root of x squared, which is the absolute value of x, but since we know that x is greater than 0, as it was told to us in the beginning, we can simplify that just to x. We can then express h, the length of h, in a similar manner. The difference in its x-coordinates is 0, but we're going to add that to the square of the difference in the y-coordinates. So we get 0 plus y squared, which is the square root of y squared, or the absolute value of y. Now, it's important to note that this xy here comes from the x in 9 minus x squared and the y, which is 9 minus x squared. So this point really, we can say instead of at xy, it's at x comma 9 minus x squared. So I can substitute in h here for y as 9 minus x squared. So the height is the absolute value of 9 minus x squared. But again, x is a positive number, right? So if I put a positive number in here, and if I put a positive number in here, I'm going to get exactly 9 minus x squared. I'm going to get a positive value because it's not going to be bigger than 9 because it's on the x-axis. Yeah. Okay, now area is equal to base times height. I'm sorry, that's not true. Area is equal to 1/2 base times height. My b is x, and my height is 9 minus x squared. And then of course we could multiply this out, and we would end up getting 9 over 2x minus x squared, x cubed over 2. So that is the area in terms of x, as a function of x. Alright, I'm going to do one more problem, which is a little bit more tricky. Inscribe, which means to draw inside, a right circular cylinder of height h and radius r in a sphere of a fixed radius r. Express the volume V of the cylinder as a function of h. And it's going to give us this all-important information that the volume of a right circular cylinder is equal to pi r squared h. So if I'm going to write the volume as a function of h, that means I can leave the h, but I need to, come on. But I need to replace r with an expression of in h. I need an expression in h and big R. Big R, by the way, is a constant. It says that it's a fixed radius, so it's not a variable. It's actually a constant. So we could put a number in there just to play if we wanted to, but it's basically what we're saying is that even if R ends up in our formula, the volume isn't going to be dependent upon that because it's a constant. Alright, so let's draw a sphere, and let's inscribe a right circular cylinder inside of it. So this is our sphere. Okay. And it has height h. So the right circular cylinder has height h and radius r. So the radius of the cylinder is this piece here. And the radius of the sphere comes from the center of the sphere and goes out to any point. For convenience, I'm going to make it come right here. So that's big R. Notice that we get a right triangle right here. It turns out that this distance is 1/2 h. Because the entire cylinder is h tall, and if we're going to go from the center up to the top, we get half of that. Alright, because we have a right triangle, by the Pythagorean theorem, we could say that big R squared is equal to little r squared plus 1/2 h squared. And then remember, we're trying to express r, little r, in terms of r and h. So what we're going to do is solve for little r. So we get r squared equals r squared plus 1/4 h squared. I can subtract big R squared minus 1/4 h squared equals r squared, and then we'll say it's equal to the square root, the positive square root, only because radius is a positive number. Okay, now we're ready to write the equation of our volume in H and R. So again, the volume is pi r squared H. So that's pi. Now instead of r, we now have the square root of big R squared minus 1/4 H squared, all being squared, times H. The square root squared, of course, is R squared minus 1/4 H squared, H. And we could, of course, go a little bit further and say that we have pi h r squared minus pi h cubed over 4, right? If we multiply that h inside and the pi inside. All right, now I'm going to give you a hint on your homework problem that is similar to this because you watched the whole video. Hint on the homework problem. I think it's the second to last problem on this section. That problem says that you've got a right circular cylinder inscribed inside of a cone. So a cone looks like this, and we've got a right circular cylinder inscribed. The height of the cone is big H. The height of the cylinder is little h. The radius of the cylinder is r, and the radius of the cone here at the bottom is big R. Yeah. So here's the hint. With both radii, we create two right triangles. We want to express the volume of the cylinder, which is again volume equals pi r squared h, as a function of r, this time, not h. And it can have big H and big R in it because they are constant, or fixed, because they are fixed again. What you want to do is use the ratio of sides of similar triangles for this. Our two right triangles are similar to each other. We have the big one with R as its base and H as its height, because that's the height of the cone. And then we have the little one that has little r as its base. And it's going to be up to you to find the height here. So I'm talking about the height right here. Find. And then use ratios of sides of similar triangles in order to help you set up the equation.